So estimator, what it will do, it will create a circuit for this with proper rotation, with proper measurement. It will get the probability distribution or PMF, whatever you say, calculate the expectation value from that PMF. It will create another circuit for this group with proper rotation, and it will run the circuit. It will get the PMF, and it will calculate the expectation value from here. So the PMF is definitely taken into consideration. Although estimator kind of wraps around it and doesn't show us exactly what is going on underlying. But what we just discussed, this is what goes on underlying. First, you find the non-commuting groups. You group your observable into commuting groups, and you find what are the minimum number of groups required. You prepare a circuit for each group with proper rotation, Hadamard gate, S-dagger, whatever you need. Then you execute the circuit with proper measurement, you get the PMF, and then you calculate the expectation value. So this is the underlying thing that happens for a estimator, but it kind of wraps around it. I hope that answers. Okay, thank you. Okay, yeah, that's a good question. Why we have qubits 8 and 9? So it is a bit difficult.
You are live, you can continue. Yeah, you can answer this question also and then continue. Yeah.
Okay. So coming to qubit 8 and 9, there are, as I said, there are mainly two requirements here. First is minimize the number of swap gates. Now this is just a single CNOT gate. So you could have put it on 0, 1, you can put it on 7, 10, you can put it on 1, 4, 1, 2, 8, 9, so many choice. There will be no swap gates for this thing. So the first thing that the transpiler does is find one such layout which requires no swap gate or minimum number of swap gate. Like no swap gate is not possible for all circuits, minimum number of swap gates. Once you find that out, now we take into consideration the noise in the system. So 0, 1 is a possibility, 1, 2 is a possibility. I mean, let's say that I initially find that my layout is 0, 1. You can argue why not 1, 2? Someone else can argue why not 7, 10? So what the system does is it will find all these other possible layouts which has the equal number of swap gates, which to the original layout that it decided. Then it will calculate the noise profile. Whichever has the minimum noise profile, that particular layout will be given. So what has happened, I am sure here, is that it has found that 8 and 9 has the minimum noise. Single qubit noise, measurement noise, CNOT, like this noise of this connectivity, it takes all of those into account, and it has found that 8, 9 has the minimum number of noise. So it has selected 8, 9. That's kind of the underlying process to do that. Wait, there was some question. Okay, thank you. Is there any whether expectation maximization algorithm can be used to reduce the error in this case? I haven't thought of it actually. Maybe. I don't know. I really don't know. Maybe it's possible. Maybe it's possible. Try it out. This seems to be a very interesting question. Is there any physical linkage between expected values and probability outcomes? Yes, physical linkage. Let's think of this. When we think of classically, when we think of coin toss, let's say if the toss is head, I will call it +1. If the toss becomes tail, I'll call it -1. So it's just a value assignment. And if it is 50-50 unbiased, then there are equal number of +1, equal number of -1. The expectation value is 0. So I think physically the way we will interpret this is that if you and I are playing playing a game, that if I'll toss a coin, if it is heads, I'll give you 1, or say, think in my terms, if it is heads, it is +1. So you will give me 1 rupee, I gain. If it is tail, I'll give you 1 rupee, so -1, I lose. If I repeat this many times, then the expected gain or loss is 0. This is kind of the physical linkage, and this physical linkage will come from the problem domain. Just like I said for this coin toss, say if it is a graph problem and I am thinking of some assignments, say zeros and ones that will have the minimum, say, vertex cover. So it will return me the probability distribution, will return me that what are the different assignments and with what probability my algorithm is returning that assignment. And the expectation value will tell me that if I follow my algorithm, what is the average or the expected vertex cover for that graph. So there is definitely a physical linkage, but it will come from problem to problem. Hope that answers your question. Okay, thank you. Let's take a break and we can come back.
Dr. Ritajit, if you are free, if you are ready, we can continue. So anyway, you can.
Yeah, can I just take 5 minutes?
Yeah, sure.
Okay.
We'll
Yes.
Hello, sir.
Hello.
Sir, I have joined from another account, but it is just showing me not as a panelist, but as an attendee. Can you
Yes,
make me a panelist?
we have
I can see what actually, finally.
what is the name that is showing, sir?
It
Yeah,
should be Ritojit Mujumdar.
right. We have added, sir. Yes,
Okay, thank you. Thank you so much.
yes.
Yeah.
Okay,
Okay.
you are able to access the pad now. Yeah, that's great.
Yeah. So that is actually very good.
Thank you, sir.
Should I get started?
Yeah, yes, please, sir. Yeah, please go ahead. You can extend your time till whatever you would like to, and especially answering the queries of the participant, right?
Yeah, sure. I hope I won't take too much time.
Right. Sure, sir.
Okay. Welcome back. And finally, a good thing is that I have my iPad working, so I can actually show something in a proper way of writing than just typing on a doc. So let's think of errors now. So we saw that previously we were using fake backend, and there are different kinds of errors. Um, what are the kind of errors we have? Say when we want to do measurement, there is an error in the measurement. When we want to do gate operations, the gate operations are noisy. When you prepare the qubits, the qubit preparation is noisy. When you create a qubit in some excited state, they have a tendency to actually release energy and go down to their ground state. So you cannot even retain the state of a qubit properly. So there was a very funny joke that goes around. I don't know if any of you have seen that someone says that, I have a quantum computer, and the other one is saying, yeah, good for you. But your quantum computer is broken in every possible way simultaneously. So all these errors exist together. I remember using this for my PhD thesis defense, which was again on noise mitigation and all those kind of things. Um, so what we will come to today, unfortunately, I couldn't write the expectation parts here, but let's move on. And we want to see the effect of measurement error, and particularly measurement error mitigation, which is very simple. And you will see like exactly how simple it is, and you should be able to start doing it immediately after this class ends. So let's think of a general quantum circuit. Say I have a general quantum circuit. What does it look like? A general quantum circuit, what does it look like? It has a set of qubits, q0, q1, up to some qn. It has some gates, say some single qubit gates, some 2 qubit gates, say, oops, some gate here, and so on. And finally, we measure. So this is kind of the meter is kind of the universal sign of measurement in quantum. Now, as we just discussed, everything here is noisy. What we will consider for the rest of this talk is when I am preparing these qubits, all the qubits start in 0. We know that in a quantum computer, all qubits start in 0. But that is not always the case. The preparation can be erroneous. So there can be noise coming from state preparation because you prepared the circuit wrong. State preparation. There can be noise coming from the measurements. You are doing the measurements wrong. We will see precisely what that is. Measurement. Now think of it. If I give you a qubit and you don't do any gate operations, you just measure and you get a wrong outcome, is it possible to say that whether the wrong outcome was because the qubit was prepared wrong, measurement was correct, or qubit was prepared correct, measurement was wrong, or both of them was wrong? Not possible, right? We only see the outcome. So it is not possible to know whether the noise, we are not thinking of gates at this point. We will not think of gate today. So whether the noise is coming from the incorrect preparation of state or incorrect measurement or both. So what we do is we take both of them together. They are something mathematically called gauge equivalent, and we just call it state preparation and measurement error, and this is together called span. State preparation and measurement. We don't want to distinguish between them. No point distinguishing. We just want to get rid of those. Currently in quantum systems, these are in the order of 10 to the power minus 2, and these are one of the most dominant errors that we have in a quantum computer. If you go to the IBM quantum platform and see the different noise characteristics, you can see the different errors that we have. You will see the single qubit gate errors are in the order of 10 to the power minus 4. Currently, 2 qubit gate errors are also in the order of 10 to the power minus 3, but the spam error is in the order of 10 to the power minus 2. So it is one of the most dominant error that we have. But what we will see is that we have very nice mitigation technique that can help us get rid of this spam error almost exactly. Almost exactly. So what we usually do is we kind of say that let's forget that there is any state preparation error, put all the liabilities on measurement. So when we say spam error, sometimes when I say spam error and measurement error, I mean them equivalently. That we sometimes say that, okay, let's assume that we cannot distinguish between them. Let's just say that state preparation is perfect. It is the measurement which is the culprit. So this is something that we do. So from now on, whatever we will discuss, we will say that it is the measurement noise. So what is measurement noise? It is simply very classical. So let's say that I ask some of you that give me a number between 0 and 1, not between 0 and 1, either give me 0 or 1. Some of you come up and say that, okay, I choose 0. You said 0, I write down 1. This is precisely measurement error. The system is in some state, the measurement is writing something different. So this is precisely what measurement error is, and it is given by, it is mathematically modeled. It is, so you can understand there is nothing precisely quantum about measurement error. There is, but you can mathematically abstract it out and say that, okay, this noise is classical because you said 0, the quantum state was 0, I wrote it down as 1. So you can always think of this error as a classical error. So the way we model it classically is that if your system is in 0 with probability, say 1 minus, I'll come to what these are. Let me just write it down. 1, 1. So what it means basically, when you start with 0 with probability P1 given 0, it means what is the probability that you end up writing 1 when the state was actually 0. This is what it means. This is basic classical conditional probability. Sorry, not audible. Um, okay. Okay. Thank you. Yeah. So this is basically classical conditional probability notation, nothing else. That if I am in the state 0, then what is the probability that I end up writing it as 1? This is what this means. The other, so this is the probability here, that when going from 0 to 1, I prepared in state, but my state was actually 0, but I end up writing 1. And what is the probability that error doesn't happen? That is 1 minus P of 1 given 0. right? This is for the 0 part. Similarly, if I prepare my state in 1, what is the probability that I end up writing it 0? That is given by probability of 0 given 1. And what is the probability that I write my 1 as 1? That is 1 minus probability of 0 given 1. That's all, right? Now, what is done? Again, we will do some mathematical abstraction and we will define something called an assignment matrix. Often in short, this is called an A matrix. So what is an assignment matrix? It is just a stochastic matrix. Here you can think 0, 1, 0, 1. Just follow the convention here. This means, so the columns means that it is prepared in this state. So when I write 0 in my first column, it means it is prepared in 0. The state was actually 0. And this row is the state was in measured. So when I write this down, this is probability of 0 given 1. Because the state was prepared in 1, but I measured it 0. So what is that value? What is the probability of 0 given 1? P 0 given 1. So what will be 0, 0? This is 1 minus probability of sorry, 1. Let's first come here. Sorry. Let's first come here. So this is that I prepared this in 1, I measured 0. So this is probability of 0 given 1. What is the probability that there was no measurement error? That is simply 1 minus probability of 0 given 1, right? So the things add up, the columns add up to 1. Similarly, when I look into this position, what it means, the system was prepared in 0, but it was measured at 1. What is that? That by is probability of 1 given 0. What is the probability that such an error didn't occur? This is my assignment matrix. It's a stochastic matrix and the columns add up to 1. The rows doesn't necessarily add up to 1. Depending on certain values of P0 given 1 and P1 given 0, they can add up to 1, but it doesn't necessarily add up to 1. It's a stochastic matrix where the column is stochastic. So now what we can say is the way we will mathematically approach this. Let's say that I am starting with the state 0. So what is the my state is originally 0, and we know that its vector notation is 1, 0, right? We know that its vector notation is 1, 0. What we will mathematically think, again, what we will think is that when I am measuring the system, my measurement is noisy, we know. But what we will think is my measurement is perfect. There is no noise here, no problem here. But after measurement, this A matrix sits and it kind of messes things up. This is how we will mathematically model it. We know that the measurement is imperfect, but the imperfect measurement, so if I say this is my imperfect measurement, this gets modeled as a perfect measurement followed by this A matrix. And I get a noisy outcome, P noisy. I get a noisy outcome. So what I can write mathematically is that my P noisy is basically A times P ideal. Correct? Now, the point is that what we get is P noisy. We don't get P ideal, because if I get P ideal, I am done. So what I get is P noisy. So I need to find P ideal from P noisy. How to do that? Sorry, simple. How to do that? Very, very simple. My P ideal is A inverse P noisy. That's all. That's all measurement error mitigation is about. As simple as this. But there are a few more things that we need to think of. Let's take an example. Okay, let's take an example. Examples make things clear. But the main idea of measurement error mitigation is this. If you know a matrix, just you already know the noisy outcome, you know a matrix, just invert the matrix, multiply, and you get the ideal outcome. Let's say that I have a quantum circuit, 2-qubit quantum circuit, and it acts an X gate on the second qubit, and then we measure. So we know that the ideal outcome, this will be 0, it starts from 0, this will be 1. So my P ideal is my first qubit is in the state 0 and my second qubit is in the state 1. Sorry, I'll just look into this. So after measurement, in the sense the error mitigation is on classical state, not exactly. Not exactly. Just hold on a minute. This is an interesting question. Just hold on a minute for this. So if we do this, we will get 0, 1, 0, 0. And I want to calculate the expectation values of IZ, ZI, and ZZ. Again, these three commute, they are all in Z basis. So I don't really need to worry about any other rotations or anything. And if you calculate the ideal values here, you calculate the ideal values. What is IZ? We know that the state is 0, 1. So it is basically 0, 1, IZ 0, 1. And I hope you can immediately see this is -1 because Z acting on the second qubit gives Z acting on 1 gives -1. So this becomes -1. ZI, this will be +1 because the first qubit is in the state 0. Z acting on 0 does nothing. This is +1. And ZZ, again, Z on first qubit does nothing. Z on second qubit gives a -1. So this is again -1. Let's say that my probability of 0 given 1 is 0.2. Probability of 1 given 0 is 0.1. Just note these values are almost 10 times high than what is seen. We discussed that the values are in the order of 10 to the power -2, but I have just taken this value slightly higher so that it is easy to visualize what is going on and things don't go to very like low non decimal places and all. So now my A matrix, what does my A matrix looks like? This is what my A matrix will look like. 0.9 is the probability that when I prepared in 0, I measured 0, because 0.1 is the probability that when you prepare in 0, you measure 1. So 0.9 is 1 minus that. Similarly, when I prepare in 1, the probability that I measure 0 is 0.2. So this is 0.8. This is my A matrix for a single qubit. This is a 2-qubit system. So what I need to do, call it A1. A2 is also the same. A2 is also the same, the A matrix for the second qubit. So my entire A matrix is A1 tensor A2. I have already written down the values. Otherwise, this would have been a cumbersome calculation. So just agree with me on this. 18, 0.72, 0.02, 0.08, 0.18, 0.02, 0.72, 0.08, 0.04, 0.16, 0.16, 0.64. This is my A matrix. So how do we get it? Simple. We calculated the A matrix for each qubit. We know how to do that. I have these values already. I just took the tensor product and I got this. So what does my P noisy looks like? Although remember that we, as we said, we usually get P noisy, but since this is just an example, I just want to show what P noisy will look like. It will look like this 0.18, 0.72, 0.02, 0.08. Remember what the actual value should have been 0100. We see that this point is still sufficiently high, but the other values are also non-zero. And if you do the same exercise and calculate the noisy expectation values, these will turn out to be Zi will turn out to be 0.8 and ZZ will turn out to be minus 0.48. So they are way off. Of course, I have taken a very high measurement error. So they are way off. They should have been -1, 1 and -1. They are minus 0.6, 0.8, minus 0.48. So they are way off. Now, if we do A inverse, again, I have written down the values. I have done that before. So A is this. If we do the A inverse, this is what my matrix will look like. Are you already noticing something off here? There was a reason I came to this example. Think of this. Are we already noticing something is off? We are. And if you have already identified it, awesome. We are noticing something off. These diagonal values are greater than 1 and there are negative values. Yes, exactly. These diagonal values are greater than 1 and there are negative values. Why is this happening? Because the inverse of a stochastic matrix is not necessarily stochastic. So what I mean by that, if a matrix is doubly stochastic, what is doubly stochastic? Both the rows and the columns add up to 1. And here we argued that for very specific cases, this row will add up to 1. The columns will add up to 1 by construction, but the rows need not add up to 1. So this is not doubly stochastic. This is just stochastic. If a matrix is not doubly stochastic, if it is just stochastic, the inverse of that matrix is not guaranteed to be stochastic, but it is guaranteed that the columns here also will add up to 1. You can check that for all the cases here also, the columns will add up to 1, but the values can be negative, the values can be greater than 1. And this is something we see immediately. What is the consequence of this? What is the consequence of this? So now I want to calculate P ideal as my A inverse times P noisy. This was my mitigation step, right? We always have the noisy expectation value and I want to multiply it by A inverse and I can get a mitigated value. So 0.0004, 0.9998, 0.0002 minus 0.0003. This is what we will get. If you want to treat this as a quantum state, it makes no sense. It makes no physical sense because these values should be probability and we have negative values here. They add up to 1, but we have negative values here. This is something what we call as quasi probability. So if you want to treat this as a quantum state, this has no physical meaning. But if you want to calculate expectation values, this is fine. Mitigated EXP values. This is fine if you want to calculate expectation values, and you will see what will happen is IZ will be minus 0.9989. ZI will be 1.00032. ZZ will be minus 0.9992. So the point is, when we are talking about measurement error mitigation, first point, measurement error mitigation does not mitigate the noise in the system. It in no way lowers the noise in the system. What we do is we often do some classical and quantum, we put in some extra classical and quantum resource um, to get an estimate of what the expectation value would have looked like if there were no noise. So this is very important. Measurement error mitigation or any error mitigation does not lower the noise in the system. It somehow gets an estimate of what the value would have looked like in the absence of noise. For that, we need to do some extra classical and quantum overhead. What is the classical overhead here? We need to do all this matrix calculation, matrix inversion. This is the classical overhead. What is the quantum overhead here? You need to know these values. I just assumed that these values are given. You need to know these values. That is the quantum overhead. And if there are no questions for this part, we will go to the coding part and we will see how this is done. I hope this part was clear. And this is kind of the reason that error mitigation is not really useful if you want to get the final state of the system. So for example, Shor algorithm, Grover's algorithm, these are like these well-known algorithms that we have in quantum. They require the final quantum state. This is where you need error correction eventually. But for all these type of problems that I talked about, yeah, this can definitely get this can definitely get complicated if we have large observables, and but we will come to that. So that's why we have this Qiskit runtime, which doesn't require you to do all these calculations. It will do all these internally. All the codes and everything are written. All you need to do is use that. So we don't need to do this manually. So, but the point here is that for those kind of problems where you need the final state, say quantum communication, you want to know what are the bits that I communicated to you, not some expectation value. Quantum cryptography, Shor algorithm, Grover algorithm, these kind of things where you need the final quantum state. This is where error mitigation is not useful. But for problems where you are okay with the expectation value, like I said, quantum chemistry problem, graph problem, machine learning problems, for these kind of states, you can use error mitigation to actually get a better value out of your noisy values. Okay, good. Let's come to coding of this. I hope this is visible. This is the IBM Quantum experience. If you go there, you have free access, for 10 minutes. And you can see all these error information here that I was talking about. See, this is your median readout error, which is in the order of 10 to the power minus 2. The median ECR is kind of a equivalent of C0 gate, which is in the order of 10 to the power minus 3, just as I said. And this is in the order of SX gate is kind of a single qubit gate information. This is in the order of 10 to the power minus 4. So yeah, as I was saying, that measurement error is actually a problem. We will again start with our old circuit that we have seen before. This is our old circuit, and this is the same observable that we will try to get the result for ZZ, because we know that ideal outcome for that observable is +1. The ideal expectation value in the absence of noise is +1. So obviously in real experiments, when you go to bigger problems, you don't have the ideal value, but it is good for this case because then we will get to see how good this mitigation is working if we know the actual line of truth. What we will do is we will create a backend with measurement needs. So previously we created an AER simulator to run our system. We'll create a noise model inside the AER simulator. To do so, we can just call this noise model from Qiskit air.noise, create an object of noise model, and this probability of 0 given 1, this is P0G1, this is what I mean, probability of 0 given 1, probability of 1 given 0, and this is my A matrix, just as we have seen. Now I create a readout error. Readout error takes the transpose of the A matrix. It requires it to be not like sum up the column to be 1. It requires the rows to sum up to 1. So I have just used the transpose of A matrix to create the readout error. So you can see this is my readout error. It's now adds up, the row adds up to 1. What we can now do simply is we can say noise model dot add all qubit readout error, and so this is applying the same readout error to all the qubits. If you need, it is very easy to also do assign different readout errors to different qubits. That's also possible. So now I pass on this noise model to my air simulator, and you see that now my air simulator has also a noise model which applies only on measure. So there is no gate error or nothing. What we will do is we will again take my sampler, and I have defined the number of shots here to be 1000 once more, just like before. And I have created my pub, which is my quantum circuit, same old parameter here. And we will just run on sampler and get the noisy counts from here. So as you see that the noisy counts, I was ideally supposed to get only 0, 0 and 1, 1. But since there is noise, I am also getting some 1, 0 and 0, 1. So if we do this sampled expectation value to calculate the EXP val, I see I am getting 0.954. I should have got 1. This was the ideal expectation value, but I'm getting 0.954. Expected. There is some degradation in the quality because there is noise. Now let us do exactly what we did. What we did, we have the noisy probability. So this is my P noisy. I have already created my A matrix here. All I need to do is invert this A matrix. This is for a single qubit. So I need to create the A matrix for 2 qubits by doing a tensor product. I'll invert the A matrix and multiply it with the noisy counts. So I create the probability vector here. This is my probability vector. It's just the same thing. I'm just taking the number of counts, how many times I observed 0, 0 and dividing it by the number of shots. So it's simple. It's just 0, 0, 0, 1, 1, 0, 1, 1. This is my noisy probability vector. I am multiplying the A matrices tensor multiplication, that is Kronecker from NumPy, and I am getting the big A matrix here. I need to invert this matrix. So from NumPy.linear algebra, I am just importing the inverse. This is my inverted matrix. We already see that we are getting some values greater than 0, and there are negative values also. Now, simply multiply A matrix invert to this noisy probability. This is what we get, right? You see there are negative values. So this is my mitigated quasi. Once more, this makes no physical sense if you want to have this as a probability distribution. Yes, what you can definitely do is you can use this and maybe run a optimization kind of thing. Yeah, you can run an optimization kind of thing, some maximum likelihood or something, and you can try to find what is the nearest probability distribution. That you can definitely do. Okay, but there was a question, I think. Please define noise model. Okay, sure. Yeah, the noise model that we did here was, this is the readout error, probability 0 given 1 and probability 1 given 0. I have created the A matrix just as we have seen, and I create this readout error object, and I pass in the noise information here. It creates this readout error. It takes the transpose of A matrix. A matrix is like column stochastic. It requires row stochastic. So we just transpose it. Now I am just saying that add the same readout error. This is a single qubit readout error, right? It's a single qubit A matrix. So all I am saying is add the same readout error to all qubits. And then I'm just passing this noise model to AR simulator. That's how you create noise models if you want to create your own. So this is my mitigated quasis, and we get the mitigated counts from here. This is my mitigated counts. I mean, this mitigated quasis, I am just again converting this into this dictionary form. So again, as you see, this has no physical meaning. And as I was saying, that if you want to find the probability distribution, what you can do is you can run some maximum likelihood or some technique that if I have given you this kind of a distribution, what is the nearest probability distribution that you can find from this? That is something that you can definitely do. But at this form, this is not a probability distribution, makes no sense for as a quantum state. And now we do the sampled expectation value again. So I am passing in the mitigated counts, and my observable again was ZZ. So you see mitigated expectation value is 1.002. Let's see. Ideal expectation value should have been 1. Noisy expectation value was 0.95. So the error was in the second decimal place. This is also not perfect, but the error is in the third decimal place. So this is better in some sense. This is better than the noisy expectation value. This is as simple as it can get. This is the basic of measurement error mitigation using this A matrix method. Now, there is one last question that we haven't answered. The question is, even when I was doing the mathematics, I have just taken a value of this probability of 0 given 1, 1 given 0. Here also, I have put my new own values of probability of 0 given 1 and 1 given 0. How do you know these values when you are going to run on a real quantum computer? Who is going to give you these values? We need to actually find out that. That is the quantum overhead. Yeah, true, sampler. So that is the quantum overhead. This portion was the classical overhead, inverting the matrix, doing all these multiplications, matrix multiplications and all. Let's go again to our, at least my favorite fake backend, fake Kolkata. What do we want to know here? What do we want to know here? We want to know what is the probability that if I start with 0, let's take this. If I start with 0, what is the probability that I get 1? How do I know that? Let's start a circuit on 0, apply no gate, measure. Ideally, I should get 0 because I am starting with 0, but sometimes I'll get 1. That will give me, so if I repeat this many times, say 1,000 times, and if I see that I am getting 1 10 times, that will give me the probability of getting 1 given 0. Similarly, how do I get this probability of getting 0 given 1? Prepare the circuit in state 1. How do I prepare a circuit in state 1? It starts on 0, apply an X gate, measure. Ideally, I should be getting outcome 1. Again, I'll repeat this many times and I'll check how many times I am getting 0. Simple. This is what is going to give me probability of 0 given 1 and 1 given 0. This is what we will do. This thing is called calibration. So I have created my first quantum circuit. It's a 2-qubit quantum circuit. So I have created my first quantum circuit. There are no gates, as you can see. So it is starting on with 0, and I just measured it. And I have created my second circuit where I am putting in this X gate on both the qubits. So the outcome should be 1 for both qubits. I am measuring it. So this is going to give me my probability of 1 given 0. This is going to give me my probability of 0 given 1. So again, I'll run the generate preset pass manager. I have just set the initial layout. So you can give your own initial layout when you transpile. And previously we have seen that they are using initial layout 8 and 9. I have just given the same initial layout here. You can avoid also giving that. The reason I have given is that these are heuristic algorithms. So sometimes maybe it can change also. I don't want it to change. So that's why. You can transpile multiple circuits at the same time, and it's a very good practice to do so. So that's what I have done. I have two circuits. I have just created a list of both of them, and I am just saying pm.run over this entire list instead of individually. That gives me ISA-QCs. Now I create my sampler, and I'll run both the circuits. So you know that we can give a list of circuits, right? So for the first time, I am giving two circuits as a single list. Now let's call this. So there are two circuits. I'll take the first circuit. I'll call it count 0. You see, this is what we get. I take my second circuit. So this was the one which was starting with all 0. It should have been ideally all 0. You see that all 0 is still the dominant one, but there are other things also. The second circuit was starting with all 1. So let's get that result. You see all 1 is still the dominant result, but there are other results also. That is coming from measurement error. So here is one point. I have a 2-qubit information here, but to prepare the A matrix, I need the information of a single qubit. How do I do that? We do that by simply what is called marginalization in classical probability theory. So what is that? Again, remember, this is qubit 0, this is qubit 1. Qiskit reads from right to left. So this is qubit 0, this is qubit 1. If you ask me what is the probability that the first qubit is in the state 0, so I will take this, the first qubit is in the state 0, the first qubit is in the state 0. I don't care whether the second one is 0 or 1. So that's marginalization. You marginalize over everything that you don't need. And we will get 983 plus 10, 993. So divided by 1000. So that's how we get the information of a single qubit. So here for the qubit 0 actually is the second qubit. So 1 here. I am just calling this marginal counts from Qiskit.result. I am passing it count 0, which contains the 2-qubit information. And I am saying that you marginalize over index 0. So you marginalize over this, just as we were calculating. Let's look into that first and then come to P10. So you see, we just calculated this, that when we are looking into this as 0, it will add up 0 and 1. So 983 plus 10 will be 993. Similarly, when the second qubit is 1, you add up these two, 6 plus 1 will be 7. Right? We get the marginal information. This is the first qubit information. This is telling me that the first qubit, the probability the first qubit is in 0 is this, goes to 1 is this. What is the probability of that the first qubit when I start with 1, it is 1 or it is 0? I need to come here, right? Because this circuit was prepared in 1. So I should have got the outcome 1. I have done the same thing here, right? Marginalize. What is the probability that this qubit is 1? That is 977 plus 15. That is 992. And what is the probability that this qubit is 0? 8. So you see, we have got the information that we need for the first qubit. We will do the same thing for second qubit. But if you have followed this, you can easily follow the second qubit. So just to repeat in one sense what we did, we got the 2 qubit information from here. We marginalized over the qubit that we don't want. For this case, we are interested in this qubit. So we are marginalizing over 0. And we have got the information of probability of 0 given 0 and 1 given, probability of 1 given 0 and 0 given 1. All I need to do is divide this by the number of shots. We have got this information here, and now we can create our A matrix. Awesome. We can do the same for qubit 1. So it will be exactly the same. Here I was saying that marginalize over index 0. Here I will say marginalize over index 1. That's what I have done. So similarly, you get this. Similarly, you get probability of 1 given 0 and 0 given 1 for qubit 2. And you get the A matrix. Note here, previously, I had said that I had given the same value of measurement error to both the qubits. That is not always true. So you can see here we had 0.007 and 0.008. Here we have 0.011 and 0.015. So this change can happen in the hardware. So that is why this calibration is actually very important. You shouldn't go and say that, okay, I can go here. Why not just use this median readout error information? Why not use that? Because that is kind of the median information. Your actual qubit information is this, right? Now the steps are simple. Now the steps are what we have done before. I have the 2 A matrices for Q0 and Q1. I'll do a tensor product of them, get the bigger A matrix. I will do the inverse of that. I get the inverse of the A matrix. Let's run the circuit on fake Kolkata. So I'll transpile my circuit first on fake Kolkata. I'll again do the sampler.run. Now it is running on fake Kolkata on hardware. I'll do my sampled expectation value. I get my noisy expectation value 0.956. Awesome. I change it into a probability vector. This is what my probability vector is. I get the mitigated quasi distribution by multiplying this big A matrix inverse with my noisy probability. This is what we get. And then we do mitigated counts. I mean, this is mitigated count. I'm just representing it now as a dictionary. This is my mitigated count, and my sampled expectation value is 0.993. Better than 0.956 because the ideal expectation value was 1. So in summary, this was a very small circuit, and therefore, see, these gates have errors, right? Gates have errors. This was a very small circuit, and therefore only a few gates were there. Measurement error was the most dominant error. Therefore, using measurement error mitigation is giving me almost the correct result. But when you want to go for larger and larger systems, only doing measurement error mitigation is not sufficient, because then the gate error, thermal relaxation error, different other kinds of errors come into play and they start becoming very dominant. So what you can do is there are other error mitigation techniques like this ZNE, PEC, PEA, etc., which are then used together with measurement error mitigation. Measurement error mitigation is always there. Together with measurement error mitigation, you also do one of these, not all of these, one of these to get rid of all those different types of errors. And by doing so, you already know, I hope by now, that we can run circuits at what is called utility scale. So at 100 qubits, 3000, 4000, 5000 gates. With the Heron, we can run up to 5000 gates, and with around 150 qubits with Herons. So we can even run such a large circuits just by doing the proper measurement, proper error mitigation. And one of you were asking, that is very valid, that This I did by hand because it was a very small system. If this becomes, say, a 150 qubit system, would you want to do this by hand? No. So all these codes are already there. Also remember this A matrix method that we have discussed. This is the simplest form of error mitigation, and this was the first error mitigation protocol there was. Even for measurement error mitigation, now we have some more advanced techniques like this M3 and T-Rex. If you are interested, you can go ahead and look. T-Rex is the one that is actually used by Qiskit at this moment. So when you do want to use Qiskit, so let's do this from Qiskit IBM runtime import estimator v2. Remember one thing, what I said is that error mitigation is applicable only when you need expectation values, not when you need probability distribution. So although I used sampler here just to show you all the steps that is happening, sampler returns you the probability distribution. So error mitigation is not applicable for sampler. Error mitigation is applicable only for estimator. So how do you do that? Estimator equal to estimator v2 mode equal to backend. Now, see, there are two things that you can do. So we have resilience level. If you put resilience level equal to 0, there are no error mitigations. Say for some reason you want to know what is the effect of noise in your system. You don't want to do error mitigation. Resilience level equal to 0, no error mitigation. Resilience level equal to 1, only measurement error mitigation. What we saw, not this protocol, but this T-Rex protocol, but only measurement error mitigation. Resilience level 2, measurement error mitigation together with this zero noise extrapolation, or some PEA is one version of this ZNE. So if you just turn these things on, you can immediately get error mitigation done. You don't have to write any codes. So this is how Qiskit makes it very, very simple to apply error mitigation. So I hope, yeah, this is where I want to stop. I hope this was useful, helpful. Yes, I'll share the IPy notebooks. I'll share the GitHub links where they are. In this question, in fault tolerant quantum systems, true. If error correction is there, perhaps we don't need to do error mitigation. Having said that, error correction is coming. It's not going to be very late now. But does it mean that learning error correction is useless? Not really. So there was one very interesting, there are multiple papers which kind of show that you can use error mitigation and correction together to get some very interesting results. So there was one paper I remember, I think from 1QBit or someone, that was very, very interesting to me. What it showed is that, say, for those of you who know that when we do error correction, there is a concept of distance of code. In general, higher the distance of, higher the code distance, more errors you can correct. Now, but again, higher the distance, the more resource you need, more number of qubits, more gates for fault tolerance and all. So what they showed is that you can use a small distance code, then you can use error mitigation on top of it, and you can get the effect of a larger distance code. So it will not be that mitigation will like die away immediately and error correction will take over. There will be a smooth transition, and even then perhaps there will be a lot of scenarios where mitigation remains to be useful even when error correction is there. There is Hadamard test to get expected. There is, see, Hadamard test has one problem. So Hadamard test calculates this inner product kind of thing, right? Can you use it to calculate the expectation value of any observable? I am not sure. First, the second is Hadamard test have a very costly circuit. It is a controlled over a big unitary. So when you want to take this to bigger circuits. See, for smaller circuits, perhaps okay. But what is the point of running a small circuit on $1 million quantum computer? No point. We eventually want to go, I also showed 2 qubit examples, but eventually we want to go to say this 100 qubit regime, and that's where Hadamard test, since it has this controlled unitary type of circuit, it becomes very costly. It breaks down when when you transpile it, it will break down into into a lot and lot of gates, and eventually the noise coming from there will just overwhelm and you will get like white noise. There won't be any signal that will come from there. No, you cannot run a 100 qubit circuit. See, okay, here is a point. If you are thinking of a 100 qubit circuit, it depends on the circuit, of course. Say you want to know what will happen if you apply Hadamard gate on all 100 qubits. Simple, right? It's just like all starting from all zeros up to all 2 to the power 100 cases. But if you are thinking of general circuits that you want to simulate any 100 qubit circuit on your local simulator, I don't remember the exact maths here, but you can show that it is almost impossible to go beyond 50 even on GPU. On your system, whatever RAM size and things you do, unless you want to totally come up with a new instruction set architecture, change your motherboard and ask Intel or anyone to come up with new types of instruction set architecture and anything, you cannot go beyond 32 on your system. It doesn't depend on the RAM size or anything. You cannot go beyond 32. If you are using GPU, you can at most go up to 50. Beyond that, it is not possible to simulate. You need to go to a quantum computer. I don't know a lot about penny lane, and perhaps I shouldn't be saying a lot about penny lane, mainly because I don't know their case properly. Penny lane is very specialized for quantum machine learning in general. You will see even from their import they do from penny lane, import penny lane as QML. That is the general import that they do. Penny lane is not meant for generalized things. As far as I know, they don't have estimator like that. They do have something for QML type, but nothing as generalized as Qiskit has. I'm not very sure how do they address this issue. Maybe some manual calculations and something, but don't take my word for it.
Yeah, if there are any questions, we will quickly summarize. Otherwise, we'll conclude for the day. You have had a practical demonstration. Sir will share the Jupyter notebook and the lecture notes that is there for today. And hopefully, we have had a very meaningful time. And of course, you have sacrificed your time, and hence you got the best of it. Thank you so much, sir. Ritajit sir, on a Sunday afternoon, you also have given your siesta time for us. That's a great effort. And hopefully, we'll hear from Ritajit sir in the next QT-05 also. So we'll continue to listen. And most of the teachers are very happy to come back also to the courses because of the enthusiasm that participants are showing. And it's a win-win situation for all of us here. Yeah, I think there's a question, sir. You could take it.
Okay, well, which thought is this about, Professor Hopes? If you can write the
Mr. Natarajan, can you be more? Can you give more details, or can you mention which thought, which insight? Which can you explain a little bit in detail? Yeah, sure, sure. We'll wait. No problem. Natarajan.
I mean,
Yeah, Mr. Natarajan, you can unmute and speak.
yeah, I think he already, yeah.
Yeah, can you unmute and speak? You have typed also, right?
So, okay, I mean, I don't really know. I haven't unfortunately seen this. Yeah, I mean, see, there are many people, even Einstein was not very comfortable with this notion of probability, right? But if you have seen Bell inequality, or perhaps you will see it in some, I think QT-05 or 06, one of them. Um, so the point is that Bell theory shows that some kind of entanglement is there, and there are, I know many, yeah, if he's from the school of hidden variable, I mean, that is something that I really don't bother a lot about. Those are questions that most of these foundational physicists are looking into. And some of them definitely say that, okay, quantum mechanics is not complete, and there is perhaps a more broader theory that can explain all of those. If there is, there is, but as per quantum computing is concerned, it doesn't hurt, right? I mean, quantum mechanics is giving awesome results, and if it shifts from probabilistic approach to deterministic approach, that's also fine, doesn't matter, as long as at this moment quantum mechanics, quantum field theory, these are kind of the best descriptions of nature that we have. Quantum computing is working. So, and again, I am not such a foundational physicist, so I am really more interested in the application part, and as long as that is working, I am very happy. And if some new theories come up, awesome.
Yeah, I think same thing with the nature-inspired algorithms. The algorithms are giving good results. We don't have a very strong mathematical background, but as we are using and we are able to get the results, we are going ahead. So yeah, there is still a little bit of some question that is there. However, we can do that.
Yeah.
Yeah.
So, okay, coming to real computer or fake simulator, see, as I said, that when you are not doing noisy simulation, you can at most go up to 32 qubits on your laptop. If you are going to do noisy simulation, the best you can go up to is 12. Even in 12, you will see your system is getting heated and your kernel will start dying. All these things will happen. So the best way really, I think, is to do that. You first test out your code using real noiseless simulator. You test that everything is working fine, what you are expecting it to work. You test out what the effect of noise will be for a small circuit, 10 qubit or something. That's the best you can go for fake simulator. Then for your actual results, you go to a real hardware. That's kind of the best approach for this. It is a good situation. Yes, it's definitely a good practice to use sampler and estimator. Um, yes, there are situations where both are needed. For example, think of these variational algorithms. Again, I don't think you have gone through variational algorithms, at least not in this course. You may know this. Um, so in variational algorithm, what we do is that we keep tuning the parameters till we find a good set of parameters. When we do that, for tuning the parameters, we need expectation value. That's where we use estimator. Once the best parameters are known, we often go for finding the state. That's where we go for sampler. Can you let us know when we need them? Some other real examples? We just need them to even run. So if you are going to if you want to get expectation value with the minimum number of circuit execution, you want estimator, even if you are doing noiseless simulation. If you want to get the probability distribution, you need sampler. So sampler and estimator are the primitives. They are kind of the wrapper which sits between you and the quantum computer. You have to use them. So yeah, you have to use them, but there are other usefulness of them as well, like error mitigation and all. There is no cloud simulator which is capable of running 100 qubit circuits. Again, generalized circuits. You can always come up with 100 qubit circuit examples whose outcome is very easy to know. Those circuits are not physically interesting if you already know the outcome. There are no cloud simulator, no normal simulator that can run 100 qubit circuits. Why noise will be there in simulator? There won't be noise in simulator. If you can use ideal simulator like I was doing air simulator, there is no noise in air simulator, right? But what I did later was I injected noise in air simulator because I wanted to know what will happen when I go to real hardware. On real hardware there is noise, so it's always sometimes a very good practice to just test out what happens in the presence of noise. Does your algorithm totally break, or does it still give a sufficiently good result? That's why we inject noise on simulator. Otherwise, there is no inherent noise in simulator. This is, I don't know how to answer this. Are we constrained to live with circuit-based quantum computing? What other type of quantum computing you want? There is this annular type of quantum computing that kind of says that you want to um, vary the Hamiltonian over time. These are the main two types of quantum computing. One is annealing, that varies the Hamiltonian of a system over time and then finds the ground state, or starts with the ground state of a Hamiltonian, varies the Hamiltonian, and the ground state also changes. Otherwise, you have this circuit-based quantum computing. Because the very fundamental notion we have is represent a state using a wave function. Yeah, I mean, that is the notion, right? That a wave function has some probability associated with it. So yes, I mean, as long as we don't come up with a super theory that kind of is deterministic or everything, this is the best that we have. Yeah, this is a good question. So to summarize the situations, see, ideally, if you need only expectation value, in general, error mitigation is sufficient. But at the same time speaking, if you want to run, say, 1,000 qubit or 10,000 qubit circuit, that is where even error mitigation can start having a lot of overhead. So you may wonder that should at that point, say at 10,000 qubits, maybe it makes more sense to get the state with error correction and then calculate the expectation value classically, just as we were doing in the beginning. But at least in the utility regime that we are in now, error mitigation is sufficiently useful, but only useful when you are okay with the expectation value of some observable. If you want the final quantum state, you need error correction. That's like the first thing that uh, more useful, less useful. I mean, you can think in that way about this. And one of the examples that I was saying where both of them can be used together is that paper from 1 qubit that I immediately can remember, is that you can use error correction to get the effect. So you create a small distance code that has some resilience against noise, not as good as you would want. So maybe you want to design a distance 11 code, but that will require a lot of resource. So you design a distance 3 code. It is still resilient to noise, but not as resilient as distance 11 would be. So what you can do there is you use that noise resilience coming from error correction, apply error mitigation on top of that to get an effect that of that d equal to 11 error correcting code. This is one example I can immediately remember. Maybe there are others. Yeah, quantum annealing. D-Wave uses this approach, but note that it is only useful for optimization type of problems. If you have any other problem, annealing is not useful. This is a difficult question to answer. It is relative, right? It depends on your perspective whether it is sufficient for research works or not. any online simulator or any simulator will allow you to go up to 32 qubits. And if you allow GPUs for your simulation, you can go up to at most 50 qubits. Now, what do you mean by sufficient for research work? That is again like your perspective, because ideally when you want to go to quantum computer, see, if I tell you that can you design a quantum sorting algorithm, this is not a great question because we have very efficient sorting algorithms. We don't need to go to quantum computer for a sorting algorithms. So if you are kind of thinking that I want to simulate quantum systems, well, if you can efficiently simulate your problems, why do you even want to go to a quantum computer for that? A quantum computer is useful when you go beyond what is possible to simulate. That is where you are doing proper science. You are going beyond what is done by simulators. Okay, yeah, like definitely. You that's like any perspective you can have. You can always like Circu more than Qiskit. That's definitely acceptable, and you can of course use it. But again, since I am coming from IBM, I would perhaps say a bit more about Qiskit. But if you also see the recent poll by Unitary Fund, 76% or more people said that Qiskit is better and they prefer using Qiskit. And there are recent benchmarking papers, and the codes are also available. Just go and search for bench press. The codes, the circuits are available, which shows that Qiskit is way, way faster than Circu or any other existing SDK. So yeah, but that's your choice. Yes, error correction should be at the hardware level, definitely. Okay, so the question is that at this moment, if you are facing compatibility around different libraries, there are certain libraries in Qiskit ecosystem. Qiskit ecosystem is not maintained by IBM. So if you are using Qiskit ecosystem, it may not be compatible with what the Qiskit is doing now. But at the same time, I would say that if you, so for example, if you are using stuffs from machine learning, that is what that was on Qiskit Nature maybe, or Qiskit Machine Learning. If you are doing stuffs from chemistry, many of those stuffs have been now transferred to Qiskit.circuit.library, and you should be able to use those. Go and look into the IBM quantum learning platform. We put in a lot of high level tutorials there for different problems that you may want to solve with the best practices. And all of them use just Qiskit. You will find problems from optimization, from chemistry, from machine learning, different things. So just take a look into those things. Hopefully that will help you if you are having this compatibility issue at this moment. I am not very sure if entanglement have bearing on measurement errors, because the way measurement errors are defined, they are errors coming from the measurement apparatus, not the state of the system. So in that sense, I would say that no, entanglement does not have an bearing on measurement error. Okay, so if you mean between qubits, yes. Okay, this is actually a very nice question, and it's a very interesting question. Measurement errors can be correlated. So if measurement errors are correlated, then error on one qubit can affect the error on another qubit. That is kind of some entanglement between measurement apparatus. And if that is true, then the way I created a matrix by taking the tensor product of two individual qubits, this does not hold true. But the reason I did that is, at least for IBM quantum systems, it has been tested rigorously that such a correlation is almost zero. So measurement errors are, for all practical purpose, we can assume that the measurements error are independent of one another, and therefore such tensor network approach for a matrix will work. To solve NP-hard problems, see, there are no use cases that immediately show that quantum computing can solve NP-hard problems better than classical computers. But having said that, those are the problems definitely that we should be targeting, because we should be targeting problems that are getting difficult or intractable from for classical computers. That's where quantum computers have a role to play. So those are definitely the problems which we should be targeting and trying to see whether quantum can give a better use case. Having said that, just one point here is, if you know of Grover's algorithm provides a quadratic speed up over an NP-hard problem. But it also shows that that quadratic speed up is the best that you can do. So you cannot have P equal to NP, at least coming from Grover. Grover does not say P equal to NP in quantum, but some speed up is definitely given there using Grover. Not necessarily. So coming to the last question is that quantum computers will be quantum computers will be most useful when you are fine with probabilistic values. No, not true. So you will come across many algorithms, particularly in this QT-05, 06 kind of things, where you will see that you can design a quantum computer in such a way, a quantum algorithm, not a quantum computer, sorry. Quantum computer is by nature probabilistic, but you can design a quantum algorithm in such a way that the outcome becomes deterministic. It is not probabilistic. Any quantum algorithm that we define, even the quantum chemistry and type of things where I'm saying of expectation value, we ideally want to make it as deterministic as possible. Sometimes it's not possible, so there is some probabilistic nature to it. But yeah, I mean, that is not really where quantum computers will be useful, because in principle, it is possible to design algorithms that gives exact deterministic value even from a probabilistic quantum computer. Uh, can you suggest best practices to use Qiskit for quantum computing? See, I haven't really worked on linear or nonlinear partial differential equations. But you know, Qiskit is an SDK, so if you have an algorithm ready, mm, I'm not sure why it shouldn't work on Qiskit. If it is such that you have many complicated unitaries which you don't know the exact quantum gates, those are required, you can just prepare the unitary. This is possible to do in Qiskit. You can give your own unitary operator, you can define your own unitary, pass it to Qiskit, and Qiskit will break it down into the gate set. So even if it comes down to such a situation that you know the algorithm, you know what unitary to apply, but you don't know what are the quantum gates that will be required, like those basis gate sets, that is not a problem. Qiskit will handle it for you. So uh, yeah, I don't have any better answer for this, sorry, unfortunately. See, if you want to think of platform, I will always say Qiskit. As I said, like more than 76% people throughout the world has said that they want to use Qiskit for their use cases. It is actually very user friendly, and we have a lot of tutorials, courses, and everything to help you out in every way. Um, so you have been seeing Qiskit for at least this session, right? It's, if you know Python, you know Qiskit. It is extremely simple. It is extremely intuitive. So, and definitely user friendly. And at the same time, you get this 10 minutes free. And if you are thinking, I know I have heard from many people that, oh, 10 minutes is nothing. Just run your circuit once. Quantum computers are fast. It takes, if you are not going to run 100 qubits at this point, if you are going to run say 10, 12 qubits to start with, it will take 4 to 5 seconds, less than 10 seconds to run one circuit. So now think that you have 10 minutes, how much work you can do. So I would definitely say give it a try.
Thank you so much, sir. Yeah, the questions will keep flowing, but yeah, I think somewhere we'll have to break it. And yeah, we will be available for any questions that you may have. Otherwise, also we can post it to sir and get his feedback. So, and then he'll continue with us in QT-05. Most of you will be there also. So we can have some more, at that time, it will be more of algorithm implementations, which we'll see. So, and more of this thing also will be at two. And of course, Penny Lane, we have seen the example of machine learning last time when it was introduced. This time we have computer vision as an example case study on Penny Lane. We look at that implementations on, I think it is on 5th of June. So please be glued to that, connected to that. So you can see how Penny Lane is there. So we are anyway giving you multiple this thing. And of course, we have CDAC people coming on 4th and 6th. They will be speaking on QSIM. So you'll have a flavor of everything, and then you can easily choose. And of course, as we have discussed more on Qiskit, so I think that's where we will also look at. So yeah, we'll conclude. I think this may be the last question. Sir, you would like to take it, or quantum cryptography algorithm implementation?
I am not very knowledgeable in this direction. If Mustafizur has any other lectures with you, or you can get in touch with Mustafizur for this communication type of questions. He's
Sure,
way more
sure.
knowledgeable that.
We'll do that. We'll do that. You can post the question to me in the WhatsApp group. I'll get the feedback for you, right? So thank you so much. I think Dr. Shivansh also joined. Dr. Shivansh, you can conclude.
Yes, sir.
And then we can close for the day. Yeah.
Thank you, Majumdar sir, for this very interesting session. And thank you, Pili sir, for being with us. I hope the participants, even on a Sunday, the participants took time. And of course, Majumdar sir and Pili sir also took time out of their busy schedules. Thank you, both of you. I think we can conclude this session now.
Yeah. We have gone by 48 minutes extra. So that's, thank you so much. Yeah. Thank you all. And we'll meet tomorrow at 2 o'clock. Yeah.
Yes, sir.